In today's module, we will be talking about some basic properties of functions. We will be talking about what does it mean for a function to be even, odd, or neither of these two. We will be talking about what does it mean for a function to be 1:1, onto, or bijective. What does it mean for a function to be continuous differentiable? We will see how to compose two functions, and we will see what does it mean for a function to be invertible. So these are fairly abstract concepts, but not really if we look at them through examples. So let's start with the first one, which is even or odd. So even functions and odd functions, we actually saw them already in the last module where we graphed them. If you recall, we plotted. So we are first talking about even and odd functions. So in the last module, we saw how the function y is equal to f of x is equal to x squared versus x looked like this, whereas the function f of x is equal to x cubed looked something like this. So if you notice what happened here, if you take the value of x is equal to +1, and if you take the value of x is equal to -1, they give you the same y value, which is +1. In this one, if you take the value of x is equal to +1, and if you take the value of x is equal to -1, you get different values of y. The y for this one is -1, but the y for this one is +1. So we can write this in an abstract way, that here f of minus x is equal to f of x for all x. This is a notation that you will see frequently in math books. It's a compact way of writing for all. I will also be using it. So f of minus x is equal to f of x makes it an even function. So this is our even function, while f of minus x is equal to minus f of x makes it an odd function. And you can see why this is the case for x squared. So f of minus x would be minus x whole squared, which is the same as x squared. So it satisfies this property. While over here, f of minus x is minus x whole cube, which is minus x cube, which again satisfies this property. So this is the central idea about even and odd functions. They are rotated around the axis when you change the value of the number on which you are operating. And as we said, we are restricting ourselves to only real valued functions. Of course, this would be more complicated if you were looking at a function defined on a complex domain, but we are restricting ourselves to real valued or simpler functions. So now let's see some more examples of even or odd functions. Anything that looks like f of x is equal to x squared plus x to the power 6, only even powers, for example, is an even function. You could very well put x squared plus 8x to the power 8. That's also even. Cosine of x is an even function. Odd function would be f of x is equal to x cubed plus x to the power 131. That's an odd function. Sine of x is an odd function. Now let's look at some example of neither. The simplest one that comes to mind is x squared plus x cubed. If you have mixed odd and even functions, you can check, and I invite you to do that, is that this is neither even nor odd. Another example would be e to the power x. This is neither even nor odd. So that is a very quick introduction to even and odd functions. Let's move on to the next one. So we just did even and odd. Now let's move on to the next one, which is 1:1, onto, and bijective. So these sound complicated, but they are actually quite simple. Let's try to write them down. So 1:1, also known as injective. We'll write it down in a general way, and then I'll give you some intuition. A function that takes you from some domain x to a range y is injective if for all x and x prime belonging to the set x, to the domain x, f of x is equal to f of x prime can happen only if, this is a notation for implies, or only if x is equal to x prime. So what does it mean geometrically? If you have a, let's say we have this function that we drew over here, x and f is equal to x squared. And let's look at the value of x. Let's say our x prime is -1, and let's say our x is equal to +1. So we know that for these two values, f of x is the same. But that does not mean that x prime and x are the same. They are different. So f of x equal to x squared, if it goes from real numbers to real numbers, is not 1:1. However, f of x, let's do it on the next page. F of x is equal to x cubed, going from real numbers to real numbers, is 1:1. If you recall that plot, as soon as you know the value of the function, you can directly say which x was it coming from. There is no ambiguity in that, right? That's the whole idea. Knowing the value of the function tells you where it came from. And you can also actually make f of x is equal to x squared 1:1 if you restrict the domain and the range to go only from positive real numbers to positive real numbers. On the right side, the range is obvious that it is positive real numbers, because x squared can never be negative, right? So we know that it is always going to be positive for the range. But for the domain here, we are allowing negative as well as positive numbers. So what if we say that, no, we don't care about this side. We are going to look at the function only in the positive domain. Then this is 1:1. There will be homework problems where we go and look at a variety of functions and see whether they are 1:1 or 1:2. So, so that's 1:1. Now let's look at the definition of 1:1, which is also called injective. Now we will look at onto. What does it mean for a function to be onto, or surjective? If these terms sound funky to you, don't blame me. I don't know why they were defined this way. I guess there might have been some motivation in Latin or Greek, I don't know. So onto means that a function, again, from x to y is onto if for all y belonging to y, there is a x such that f of x is equal to y. So if I give you a certain value in the range, you must have a certain value of the original domain, which the function takes you from the domain to that value of the range. So let's look at it through examples of what it means. So again, let's consider our function x squared going from R to R. This is not onto, right? Because if I told you, let's consider f of x is equal to -100, then there is no x such that x squared is equal to -100, right? Unless you change your domain to be the set domain of complex valued numbers, then it would be possible. But if you're looking at real numbers, that is not going to be the case. And we can make it onto if we say f of x is equal to x squared going from R to only positive real valued numbers. Then for any positive real valued number, you have its inverse that exists. So that's our onto or surjective. The third one, which is bijective, It's actually really simple. It is 1:1 and onto. If a function is 1:1 and onto, that is injective and surjective at the same time, it is also called as a bijective function. So why do we care about all of this? We care about all of this, especially about the onto, you should care about, because it directly relates to the inverse of a function. If a function is not onto, you will not be able to invert it. And we will get to that in a moment. In order to understand inversion correctly, we should first look at the composition of functions. And it's quite possible that I don't do these two in this module. I will get to them later. I want to first introduce to you the basic idea of continuous and differentiable functions. So we looked at functions such as f of x is equal to x squared, f of x is equal to x cubed. And if we plotted them, you see, they looked kind of smooth, right? Everything was wonderful. There was no funky business going on. This x squared looked like this one, and x cubed looked like this one. But what if I drew you a function that looks like and then like this? So let's use a different color to make it very, very clear. So we went from over here. Actually, I did not use a different color, so let's use this one. And then we started over here. So this is an example of a discontinuous function. And you can see why it would be called discontinuous, because you have a discontinuity at this value of x is equal to 0. If you approach x is equal to 0 from the negative side, you get the value of f to be negative. And if you approach x is equal to 0 from the positive side, you get the value of f to be positive. And this could be any value. It could be +1 or whatever you wish. So that's a discontinuous function, while these two over here are continuous. Later, we will also talk about differentiable functions, where we will have to introduce the notion of the slope of a function, how to differentiate functions, and then we will look at whether the differentials of a function are continuous or not, and that will lead to the concept of differentiable function. So this is a good point to stop today's module. What did we cover? We covered even, odd, neither. We looked at 1:1, onto, bijective, and then we looked very briefly at the notion of a continuous or a discontinuous function. Next time, we will go and study what does it mean. So the differentiable bit, we are really not going to do right now. We have to do a bit of calculus to get to that. But next time, we are going to study what does it mean to compose two functions. And then after composition, we will talk about the inverse of a function, where the onto property will be important. So, and I will erase these two because we did not study these, and I will be providing extra homework problems for these concepts to be clear to you. Thank you very much.